Imagine holding in your hands a piece of paper that's over 500 years old, covered with mirror writing and intricate sketches that seem to leap off the page with impossible ingenuity. These aren't just any drawings. They're the revolutionary blueprints of Leonardo da Vinci, a man whose imagination soared centuries ahead of his time. Today, we're witnessing something extraordinary. Engineers, scientists, and passionate inventors around the world are breathing life into these ancient designs, transforming Leonardo's dreams into working reality. Leonardo da Vinci wasn't just an artist who painted the Mona Lisa and the Last Supper. He was a visionary engineer whose notebooks contained designs for helicopters, tanks, submarines, and flying machines, concepts that wouldn't become reality until the 20th century. His codices, filled with over 7,000 pages of notes and drawings, represent one of humanity's greatest treasure troves of innovation. But here's what makes it truly fascinating. Many of his designs were so advanced that the technology of his era simply couldn't support their construction. Fast forward to our modern age, where cutting-edge materials, precision engineering, and advanced manufacturing techniques have finally caught up with Leonardo's extraordinary vision. Across the globe, dedicated teams are embarking on ambitious projects to recreate his inventions, not as museum pieces, but as functional machines that actually work. These aren't simple replicas. They're sophisticated reconstructions that require deep understanding of both Renaissance engineering principles and contemporary technology. Take, for instance, the incredible work being done at museums like the Museo Nazionale della Scienza e della Tecnologia in Milan, where engineers have successfully built working models of Leonardo's aerial screw, his conceptual helicopter design from 1485. Using modern lightweight materials while staying true to his original mechanical principles, they've created a device that actually generates lift, proving that Leonardo's understanding of aerodynamics was remarkably sophisticated. But the Renaissance revival doesn't stop there. In workshops from California to Cambridge, from Tokyo to Turin, contemporary inventors are tackling Leonardo's most challenging designs. His self-propelled cart, often considered the world's first programmable robot, has been reconstructed using precise measurements from his drawings. When built according to his specifications and wound up like a giant clockwork mechanism, it moves exactly as Leonardo intended, following a predetermined path with stunning accuracy. Perhaps most captivating are the attempts to recreate his flying machines. Leonardo designed numerous aircraft, from ornithopters that mimicked bird flight to gliders with sophisticated wing structures. Modern aviation engineers, working with materials Leonardo could never have imagined, carbon fiber, titanium alloys, and advanced composites, are discovering that his aerodynamic principles were often correct, even when his execution was limited by 15th century technology. These contemporary reconstruction projects serve multiple purposes beyond mere historical curiosity. They're teaching us invaluable lessons about innovation, problem solving, and the timeless nature of good design. Engineers working on these projects often discover that Leonardo's solutions to mechanical problems are surprisingly elegant and efficient, sometimes superior to modern alternatives. Moreover, these projects are inspiring a new generation of inventors and engineers. Students and researchers involved in Leonardo reconstruction projects report that working with his designs fundamentally changes how they approach problem solving. Leonardo's method of combining artistic observation with scientific analysis, his habit of studying nature to solve engineering challenges, and his fearless approach to tackling seemingly impossible problems offer powerful lessons for contemporary innovation. As we embark on this journey through the world of Leonardo reconstruction projects, we'll explore how modern teams are decoding his mirror writing, interpreting his sketches, and solving the engineering puzzles he left behind. We'll discover how 21st century technology is finally making his 500-year-old dreams take flight, roll forward, and come alive in ways that would surely amaze even the master himself. But before we can witness these magnificent machines in action, we must first understand the extraordinary challenge that modern engineers face: deciphering Leonardo's cryptic visual language and translating his Renaissance-era concepts into workable 21st century blueprints. Picture yourself as a contemporary engineer, standing before one of Leonardo's original codices. The paper is yellowed with age, the ink faded to a warm sepia tone. What immediately strikes you isn't just the beauty of the drawings, but their bewildering complexity. Leonardo wrote everything in mirror script, from right to left, readable only when held up to a mirror. This wasn't mere eccentricity. Scholars believe he developed this technique to keep his ideas secret, to prevent casual observers from stealing his innovations, and perhaps because, as a left-handed writer, it prevented him from smudging wet ink. Dr. Carlo Pedretti, one of the world's foremost Leonardo scholars, once described the experience of studying these manuscripts as conducting a conversation across 5 centuries. Every sketch contains layers of meaning, with Leonardo often drawing multiple iterations of the same concept on a single page, showing the evolution of his thinking in real time. His drawings aren't just technical illustrations. They're windows into a restless mind that never stopped questioning, improving, and reimagining. Modern reconstruction teams begin their work not with hammers and screws, but with magnifying glasses and digital scanners. At the Smithsonian Institution, researchers use advanced imaging techniques to reveal details invisible to the naked eye. Infrared photography uncovers hidden layers of Leonardo's sketches, showing preliminary drawings beneath the final versions. X-ray analysis reveals how he corrected his designs, providing crucial insights into his engineering thought process. Take the case of Leonardo's famous aerial screw, his helicopter-like flying machine. The original drawing shows a spiral-shaped rotor above a circular platform, with 4 men operating cranks to spin the device. But what seems straightforward at first glance becomes a puzzle of mechanical complexity upon closer examination. How exactly were the gears supposed to connect? What was the optimal angle for the spiral blades? How much torque would be required to generate lift? Contemporary engineers working on these reconstructions have discovered that Leonardo rarely provided complete specifications. He assumed a level of mechanical knowledge that was common in his era but has been lost to time. This means that modern teams must become Renaissance engineers themselves, learning about 15th century materials, manufacturing techniques, and mechanical principles. They study not just Leonardo's drawings, but the entire technological context of his time. Professor Mark Rosheim, a robotics engineer who has spent decades recreating Leonardo's mechanical designs, describes this process as archaeological engineering. His team doesn't just build machines, they reverse engineer Leonardo's thought process. When working on Leonardo's Mechanical Knight, a programmable automaton designed for court entertainment, Rosheim's team had to understand not just how the mechanism worked, but why Leonardo chose specific gear ratios, joint configurations, and control systems. The detective work extends beyond the drawings themselves. Leonardo's notebooks are scattered across museums and private collections worldwide. The Codex Atlanticus in Milan contains different pieces of the same puzzle found in the Windsor collection in England or the Codex Madrid in Spain. Modern reconstruction teams often find themselves piecing together designs from fragments scattered across continents, like assembling a 500-year-old jigsaw puzzle with pieces held in different countries. But perhaps the most remarkable discovery that modern engineers make is how often Leonardo was right. His understanding of mechanical advantage gear ratios, and structural engineering was extraordinarily sophisticated. When teams at the Museum of Science in Boston built his self-supporting bridge, designed to be assembled without nails, screws, or rope, they found that it could indeed support tremendous weight using only the principle of compression and Leonardo's ingenious interlocking design. These reconstruction projects are revealing that Leonardo wasn't just dreaming impossible dreams. He was solving real engineering problems with solutions that were centuries ahead of their time. Each successful reconstruction proves that his mind operated on a level of technical sophistication that we're only now beginning to fully appreciate. Now comes the moment of truth, when centuries-old dreams meet cutting-edge technology, and Leonardo's sketches transform from museum curiosities into roaring, spinning, flying machines that prove the Renaissance master was indeed a prophet of engineering. In workshops around the world, teams of craftsmen, engineers, and historians are breathing life into Leonardo's designs using a fascinating blend of period-accurate techniques and modern precision tools. At the Leonardo III Museum in Milan, master carpenter Giuseppe Nicoli approaches each reconstruction as if he were working in Leonardo's own workshop. He uses hand tools when Leonardo would have used them, selects wood species that were available in Renaissance Italy, and employs joinery techniques that haven't changed in 5 centuries. But here's where the magic happens. When Nicolai encounters a measurement that's unclear in Leonardo's drawings, he turns to laser scanners and computer modeling software. This marriage of old and new creates an extraordinary dialogue between past and present. We use Leonardo's eyes and hands, Nicolai explains, but we give them modern tools to see what he couldn't quite finish. The process is far from straightforward. When the team at Harvard's collection of historical scientific instruments attempted to build Leonardo's spring-powered cart, arguably the world's first programmable robot, they discovered that the master had embedded multiple layers of innovation into a single design. The cart wasn't just self-propelled, it was programmable. By adjusting the angle of wooden cams, operators could make the cart turn left or right at predetermined distances. But Leonardo's drawings showed only the final configuration, not the experimental process that led him there. Dr. Mark Rosheim's team spent 3 years and built 17 different prototypes before achieving a cart that could execute Leonardo's program movements. Each failure taught them something new about Renaissance engineering principles. They discovered that Leonardo had solved problems in gear ratios that wouldn't be formally understood by mechanical engineers until the 18th century. His intuitive grasp of mechanical advantage was so sophisticated that modern computer simulations confirm calculations he had performed purely through visual reasoning. Perhaps nowhere is this translation from sketch to reality more dramatic than in the reconstruction of Leonardo's flying machines. At the Fiumicino Airport in Rome, a team led by engineer Luciano Lorenzi spent 5 years building a full-scale version of Leonardo's ornithopter, his wing-flapping flying machine. Using modern materials like carbon fiber and titanium, but faithfully following Leonardo's mechanical principles, they created a device that actually achieved brief, controlled flight. The moment of that first flight was electric. As the ornithopter's massive wings beat against the air, observers could see Leonardo's 500-year-old dream taking physical form. The machine didn't just fly. It flew exactly as Leonardo had predicted, using the wing warping techniques that wouldn't be invented by the Wright brothers until 1903. Lorenzi later described the experience as shaking hands with Leonardo across the centuries. But these reconstructions reveal something even more profound than Leonardo's technical accuracy. They show us his understanding of systems thinking that was centuries ahead of his time. When teams at the Chateau du Clos Lucé in France built his automatic bobbin winder, they discovered that Leonardo had designed not just a machine, but an entire production system. The device could operate continuously, automatically stopping when bobbins were full and resuming when empty ones were installed. This wasn't just mechanical engineering, it was early industrial automation. The reconstruction of Leonardo's mechanical knight proved equally revelatory. Standing 6 feet tall and capable of sitting, standing, and moving its arms, the knight was more than a curiosity. It was a sophisticated exploration of human biomechanics translated into mechanical form. Modern robotics engineers studying the reconstruction have found principles that directly inform contemporary prosthetics and humanoid robotics. Leonardo's knight wasn't just mimicking human movement, it was analyzing and recreating the mechanical principles underlying human anatomy. Each successful reconstruction sends ripples through the modern engineering community. When Leonardo's self-supporting bridge was tested at MIT, civil engineers discovered stress distribution techniques that are now being applied to emergency bridge construction. His paddle wheel boat designs have influenced modern amphibious vehicle development. Even his kitchen spit roasting mechanism, with its automatic speed regulation based on fire intensity, has inspired modern thermostatic control systems. These projects prove that Leonardo's notebooks weren't just the fantasies of a brilliant dreamer, but the working blueprints of history's most prescient engineer. Every gear that turns, every wing that flaps, every mechanism that moves as he intended is a testament to a mind that could see the mechanical future with startling clarity.